Hey guys, today we're going to continue on with conservation of momentum, but we're going to look at it in 2 dimensions instead of just one. So with the air track simulator that you did last time, we were looking at things that were sliding along and bouncing into each other, and they're going back and forth only in one direction, like carts on a meter stick. Today we're going to look what happens when we expand that to 2 dimensions. Two-dimensional collisions, that's what we're talking about. So we're thinking of things like billiard balls or bowling pins after a bowling ball hits them and sends pins flying in different directions. How do we handle those things? So we're looking at different types of two-dimensional collisions, and then we'll see how to analyze each of them. Okay, so yeah, what about billiard balls and bowling pins? It turns out that 2D collisions, there's really two possibilities. One, they could be elastic collisions where the two objects bounce off of each other, like billiard balls hitting each other and going different directions, or again, bowling balls hitting pins. But you can also have inelastic two-dimensional collisions, like a car wreck, a T-bone car wreck, where two vehicles are traveling along, they run into each other, and then the wreckage kind of sticks together and goes off in some direction as one mass. So we're going to look first at the inelastic. Let's see, let's just go to the camera here. We're going to do this one second, so ignore this one for now. So we're going to look at a car wreck. We have a car which has a mass of 2,000 kilograms moving to our left, and another car of mass 750 kilograms moving upward from our point of view. So we're bird's eye view here. And the speeds are here, 10 meters per second for the heavy car, 15 meters per second for the light one. And intuitively, from our own personal experience or from just our experience with the world, we know that when the cars run into each other, if they stick together in elastic collision, they're going to go off in this direction someplace. Okay, and what we want to find out is the velocity of the wreckage. Okay, the velocity of the wreckage, which is the speed and the direction. That's what we want to figure out. Okay, so we're going to use this as a reference line of 0 degrees. So we're going to try to figure out the angle above horizontal from our standpoint here. Okay. Now, the way that we do this is we need to think of this as a vector problem. Momentum is a vector. So this car, the heavy car, is carrying momentum along the x-axis, and the light car is carrying momentum along the y-axis. And when they combine, the wreckage is going to have the momentum for both of those because momentum is conserved. So the wreckage will have the horizontal momentum and the vertical momentum. So we're going to first calculate the momentum for each one of these. So for the light car, it's going to be 750. There we go, 750 times 15 meters per second. So this momentum is 11,250 units. And the momentum of the other car is 20,000 units of momentum equals P. And as I said, the wreckage will have both of those momentum. The momentum that they carry in will be conserved. So we have to make a diagram here, a vector diagram, where the horizontal momentum is 11,250 and the vertical momentum is 20,000. And we need to figure out the hypotenuse. Okay, this is a momentum diagram. So we have momentum going this way, and they add together to make momentum going up. You know what? I did that backwards, obviously. Okay, let's switch this around. So yeah, this is 11,250, and this is 20,000. And my triangle is distorted, but we'll straighten that out. Okay, so it's a vector diagram, as I said. So first, we're going to figure out the length of this by just Pythagorizing. So 11,250 x squared plus 20,000 x squared equals, we'll take the square root of all that, and we get 22,950 basically. 22,950 is the total P, the total momentum. Now that's just momentum. If we want to find the speed, we have to convert that back into velocity. So as you know, P is equal to mv, mass times velocity. Now the total momentum of the wreckage is 2,750. So we can divide 22,950, that's the total momentum, is 22 2750 kilograms times V. So when we divide this by 2750, we get 8.3 meters per second. Okay, so our speed is going to be 8.3 meters per second. Well, that is what it is. And now we need to figure out the angle. And the way we figure out angles with SOHCAHTOA. And in this case, the tangent of theta is the opposite over the adjacent. So we're going to do 11,250 divided by 20,000 equals, that is the tangent of the angle, so we need to take the inverse tangent of this number, which comes out to be 29 degrees. 29 degrees. Okay, so this angle here is going to be 29 degrees. And the speed is going to be 8.3 meters per second. Okay, and that's our answer. Now this kind of makes sense. This car is carrying more momentum than this one, so it makes sense that it would be more that direction than this direction, and that kind of makes sense. Obviously, I distorted that in this drawing, but that's all right. Now, the speed may seem kind of strange that we would actually lose speed, that the wreckage would be going less than either one of the original velocities. But when you think about it, this car slows down when it hits this car. And this car slows down when it hits this car because they're not working together in either way. So really, both cars are losing some velocity, and that's why the resulting velocity is less than either one individually. All right, so now let's take a look at an elastic two-dimensional collision. And this one, because I've been talking about bowling balls and bowling pins, here we have one. So the bowling ball has a mass of 7 kilograms. It's moving at 3 meters per second. It's rolling up. It's going to hit this rather crude drawing of a bowling pin. Did my best. And the bowling pin is going to bounce off at this angle. So initially, the bowling pin is just sitting there. So it's 1 kilogram, 0 meters per second. After the ball hits it, it's going to go sailing away at 10 meters per second at a 45-degree angle there. We want to figure out what is the velocity of the ball after the ball hits the pin. So again, from our common experience, we know that the ball is going to deflect up this direction some way. But we want to know how fast the ball is going to be going after the collision and in what direction. So the way we do this is we keep in mind that momentum is conserved, again, just like with the car crash, momentum is conserved in the y direction and in the x direction. Now, initially, the ball is going straight up on the page, and the pin is not moving at all, which means that there is no momentum at all in the horizontal component, the x, in the x axis. So that means that after the collision, there still has to be no momentum in the x-axis, meaning that whatever the pin has going sideways one direction, the ball has to have the same amount of momentum going in the opposite direction, so that the horizontal momentum balance and they add up to 0, which is how much there is before the collision. Now, likewise, in the y-axis, the vertical axis here, the ball has all of the momentum and the pin has none. Now, after the collision, the pin is going to be moving toward the top of the page a little bit, so the pin is going to gain some momentum in the y direction, and that means that the ball has to have lost that much direction. Another way to say that, whatever the pin gains, the bowling ball loses. So we're going to start off by figuring out the momentum of the ball. We got to start somewhere, so why not that? So P equals mv, and for the ball, that's going to be 7 kilograms times 3 meters per second. Yeah, we've got room here. So that equals 21 kilogram meters per second of momentum. That's what the ball has in the y direction. And as we said before, there is no momentum at all in the x direction. Okay, now the next thing we can do is to figure out the momentum of the pin after the collision. And since it's 1 kilogram and it's moving at 10 meters per second, that means the momentum is 10 kilogram meters per second. But what we really have to do here is break that momentum into its vertical and horizontal components. So here we go with trig again. So this is for the pin, and we have 45 degrees, and this is 10 kilogram meters per second. Now, keep in mind, I'm making a momentum diagram, and it probably maybe would have been better to have some mass other than 1 kilogram so that the units don't look the same, but I think you'll be able to see what we're doing here as we go along. So we need to figure out the x component and the y component of that momentum. So we use SOHCAHTOA. And we have, let's see, so sine of 45 degrees is 0.707. We're going to multiply that by the momentum, which is 10, and we get 7.1 kilogram meters per second is the momentum horizontally. And since it's a 45-degree angle, it's also going to be 7.1 kilogram meters per second vertically. That's the components of the momentum of the pin after the collision. Now, as we said before, now we have to figure out where this momentum came from. So let's start off with the vertical one. The bowling ball had 21 units, and it gave 7.1 units to the pin. So the ball in the y component, let's go say that one, is going to be 21 minus 7.1, which is 13.9. That is going to be the momentum in the vertical axis for the ball after the collision. Now, the ball horizontally, that's the x-axis, has to be the same as the pin. If the pin, excuse me, if the pin has 7.1 units of momentum that way, then the ball must have 7.1 units the opposite direction, so that when we add together the momentum of the pin plus the momentum of the ball, we get 0, which is how much horizontal momentum the system had before the collision. Okay, so now we have the vertical component of the ball's momentum and the horizontal component, and we can put those together into a diagram. We have 7.1 and 13.9. And that is the resultant momentum right there. And we can Pythagorize to figure that out. And we get 15.6. 15.6 units of momentum. Now, this is momentum, okay? It is not velocity. So now we have to convert this momentum back into velocity. Again, momentum is equals mass times velocity. So we have 15.6 equals the mass of the ball, which is 7 kilograms, times v. So v, the actual speed of the ball, is going to be this 15.6 divided by 7 kilograms, 2.2 meters per second. That is the speed of the ball. We want to do a quick check, make sure it makes sense. The ball was moving 3 meters per second, so we say it slowed down a little bit, so this looks reasonable. Finally, we have to figure out the angle. Again, we use SOHCAHTOA to do that. And let's see, I guess I should move my picture here so that you can actually see what I did. There we are, 2.2 meters per second. Okay, now for the angle, this angle here, we're going to use SOHCAHTOA again. Tangent of theta is the opposite over the adjacent, which is equal to 13.9 divided by 7.1. So we get 13.9 divided by 7.1. So this number is the tangent of the angle, so we can take an inverse tangent at it and we get 63 degrees. So theta is equal to 63 degrees, meaning that the ball is going to go out at an angle here, and this angle is 63 degrees. And again, that kind of makes sense. The ball got deflected, but not as much as the pin did because the ball has more mass than the pin does. So from our experience, this answer that we get seems to make sense. So final velocity of the ball after is 2.2 meters per second at 63 degrees. That's our answer.